We have learned that diffraction can be interpreted as a Fourier transform. Let's review how this works and take a look at some examples. Here we have an incident plane wave onto an aperture in an opaque screen. Light is passing through, it diffracts, and in the far field it forms the diffraction pattern according to Fraunhofer diffraction. In Fraunhofer diffraction, the electric field can be evaluated from the diffraction integral. Let's write it in only one coordinate at the screen. Now we can compare it with the more familiar Fourier transform between time and angular frequency. By comparing these expressions, we see that Fraunhofer diffraction is indeed equivalent to Fourier transform of the electric field at the aperture. Diffraction problems are pretty complicated for arbitrary aperture shapes. However, by using a fast Fourier transform, we can numerically calculate these integrals very quickly. The implementations of numerical FFT algorithms are available, for example, in Matlab and Python programming languages. Here's an example of a Matlab script to calculate the Fourier transform numerically. We have several pre-made pictures of the aperture, which we are reading from the file, and the Fourier transform of the two-dimensional images are calculated with FFT2 command. Basically, this is all we need to do to calculate the diffraction from an aperture. All the rest of the script is about plotting it. And let's now run through some examples and see how the shape of the aperture affects on the diffraction of light. The first image is the diffraction pattern of a square hole. We'll see that the diffraction has the main peak and then the side lobes in two different directions. Next, we are going through some series of modifications for the apertures and observe how the diffraction pattern changes when the certain dimensions of the aperture are changing.